Good morning. Welcome to this second day of our workshop dedicated to uncertainties related to geological modeling. So today we have two sessions. First one this morning dedicated to communication and application. Sorry, this is the one for this afternoon. This morning is geological surveys, organizations, and case studies. So we will touch some practical examples, especially from the geological surveys, and this afternoon regarding communication and application. I posted the link to the detailed program in the chat. As usual, if you for the presenters, if you want to send in advance your slide, just in case something goes wrong with the sharing, just send an email to Daniel, Marco, and me, please. And we can start now. It's 9 and plus 1 minute. Yeah, we can start the session. And for that, I welcome Eva Szynkaruk from the Polish Geological Survey. We will share the session this morning. Eva, please.
Thank you. Can you hear me?
Yes.
Okay, great. Thank you, Philip, for this short introduction, and welcome everyone. My name is Eva Szynkaruk from Polish Geological Institute, and I have a pleasure to chair this session today for you. This morning we have a session called Geological Survey Organization and Case Studies. Yesterday we were talking about methods and concepts and more theoretical, let's say, aspects of our work on uncertainties. And today we are going into down to the earth applications and hands-on exercises and actually real-world examples. So in this session we will have an opportunity to see how geological surveys are dealing with uncertainties in their day-to-day work, and we will see some case studies, and also we will have an Mentimeter exercises as we had yesterday that will be chaired by Daniel Marco from Euregion surveys, and we will have some space for discussion. Each presenter has like 20 minutes, 15 minutes for presentation and 5 minutes for questions after them. So please keep to this timeline. We start with the first presentation by Jan Stafleu from the Geological Survey of the Netherlands. And Jan will show us how Geological Survey of the Netherlands is employing uncertainties in their day-to-day work. Welcome, Jan. The floor is yours.
Good morning, everybody. So in this first talk of the second day, I will present the way in which we estimate and visualize model uncertainties in the national subsurface models of the Netherlands. And I will first briefly introduce you to these models, and then we will dive into the uncertainties. And the national models, there are basically 3 of them. On the left, you see our stratigraphical framework model, DGM, which consists at a stacked series of tops and bases of geological formations. At the bottom right, you see that we use the stratigraphical framework model to add aquifers and aquitars, and these aquifers and aquitars are then also populated with hydraulic parameters. So this model serves groundwater applications. And on the top, you see the GEOTOP model, which takes the upper 50 meters of the DGM, turns that into voxels, and then within the stratigraphical layers in the voxel model, we estimate lithological classes. So the general workflow to create these models is that we start with a large data set of boreholes which we interpret in terms of stratigraphy. And then for the layer-based models, we construct tops and bases using two-dimensional interpolation techniques. And basically, this is already the endpoint for the layer-based models, DGM and REGIS. But for the voxel model geotop, we return to our boreholes, classify them in terms of lithological classes, and then model lithologies or lithological classes within the framework of the stratigraphical layers. So we have an estimate of lithology in the upper 50 meters of the subsurface. So picture 2 is a series of stratigraphical units, of which the depth of each unit is uncertain. And the last step, the voxel modeling, shows the lithological distribution, which is also uncertain. So let's have a look at the uncertainty in the layer models. And in our workflow, we have two components in that uncertainty, a regional uncertainty and an uncertainty that has to do with the data density or the data proximity. The regional uncertainty is estimated using cross-validation statistics, in which we take a data point out of the entire data set, then estimate the depth of a formation at the location of that data point. Then we repeat that for all the data points, and afterwards we look at the difference between the estimated value at the data points and the true value at the data points, and that is input to calculate the regional uncertainty. And as you can see from the plot, the regional uncertainty is low where we have many of our data points. It is higher where we have less data. It is very high. Geology is complex. That is the area which you can see on the left has many faults. And it is low in parts where geology is more predictable and there's enough data. But we also want to take into account that if we are close to a borehole, if we're close to a data point, then uncertainty will be lower. That is the effect of data proximity. And to estimate that uncertainty effect, we use the variogram, the same variogram that was being used to calculate the depth of the base of the formation. And from the variogram and the distance of to the data points, we calculate a factor, the data density factor, ranging from 0 to 1. So 1 is at the data point and 0 is at a certain distance from the data point given by the variogram. And then the final uncertainty map is then a combination of the regional uncertainty and the data density factor. So you can see that we've taken into account a regional uncertainty, and close to the data points, we lower the uncertainty because we know better what the true value is. So this is very nice, and it results in a set of uncertainty maps, one uncertainty map for each of the layers in the model. But if a user looks at our model, for instance, by looking at the cross-section, he doesn't see the uncertainty maps at the same time. So how to visualize this uncertainty? I think we have part of this answer solved, part of this answer given in our geotop model. So we'll have a look at that. And I will first explain how we did that using the uncertainty of the lithological classes. But I promise that I will get back to the stratigraphical layer. So let's have a look at the attributes of our voxel model. Each voxel has the stratigraphical unit it belongs to, which is derived from the layer model. It also has an estimate of the most likely lithological class. And lithological classes are being estimated using a simulation procedure with a Monte Carlo component. So basically we have 100 model runs, each predicting the distribution of lithological classes in a slightly different way, but each of those outcomes is statistically equally probable. And from those 100 model runs or 100 realizations, we can calculate the probability of occurrence for each of the lithological classes, simply by counting the number of times a lithological class was being predicted by the model. So if we look at the same voxel, we can construct a bar graph which shows a most likely lithological class, in this case clay, with a probability of more than 50%. But you can see that other lithological classes are also possible. So the model doesn't know for sure which lithological class is in this voxel. So this is already a kind of uncertainty, maybe the best uncertainty that you can get in the voxel model. You can still do this if we look in one dimension in a vertical voxel stack. So at a single location, we look at all the voxels that are stacked on top of each other at that location. We have a nice most likely outcome, and to the right we see bar graphs of the probabilities. And for instance, at 20 meters depth, we see there's a lot of coarse sand, that's the dark yellow, and no other lithologies or hardly any other lithologies, so their model uncertainty is low. And at the bottom, close to the 50 meters bottom of the model itself, we see clay, clayey sand, fine-grained sand, coarse sand. So there the model is very uncertain what the true lithological class should be. But if we have a look at the 3 dimensions, for instance in this Venn diagram, we can plot the probability of clayey sand, or of fine-grained sand, or of peat, but we cannot plot them all 7 lithological classes at the same time. So in this case, I plotted probability of clayey sand, and I can see here that there's one layer with a high probability of clayey sand. So we can expect that model uncertainty in this layer is quite low, because I have very high probabilities of only one lithological class, but I cannot tell what the model uncertainty is for all the other layers. So to solve that problem, how do we visualize model uncertainty in one view, we have looked at the concept of information entropy, which was applied in geological modeling for the first time by our own Florian Wellman. And I'm illustrating this here in a table with only 3 lithological classes, peat, clay, and sand. And in the first example, the first row of the table, it says that the probability of P is 1 and the other 2 are 0. Then model uncertainty is at its lowest, because the model always predicts peat. The second line, the probability of peat equals the probability of clay and the probability of sand. Then the entropy, or the model uncertainty, is at its maximum, because the model cannot decide what lithological class is in the voxel. If we then go to the third example, we see that peat and clay are difficult to distinguish from each other. So they both have the same probability, but the model is sure, the modeling algorithm is sure that it isn't sand. So that gives a drop in entropy. But if we then again introduce sand only with a slight probability of 2%, then entropy increases again. So you can see that this entropy takes into account the probability distribution amongst the lithological classes, and also the number of lithological classes that play a role. So the uncertainty will drop if lithological classes have a 0 probability. But we've applied this rule to the 7 lithological classes of the geotop model and now have a single visualization of probability. Let's have a closer look. And you can see unit A, that was the unit with a very high probability of clayey sand. You can now see that indeed the model uncertainty of that unit is very low. And there's also a unit B, which is very heterogeneous in composition, and is also deeper in the subsurface, so that has a very high model uncertainty. We can calculate the model uncertainty also in an average for each of the stratigraphical units in the model. And if we plot that in a bar graph, we can see our unit A with a very low model uncertainty as a whole, as an average, and unit B with a very high model uncertainty. And we can also see, well, kind of a trend of increasing model uncertainty with depth. Depth increases from left to right. Now, I promised that I would get back to the stratigraphy. GeoTop also has the stratigraphy in the voxels derived from the layer-based model. And now we are going to look at a vertical voxel stack, and we're going to estimate the probability that a voxel belongs to a certain stratigraphical unit. So the stratigraphical units are on the left-hand side, the blue, the yellow, the brown, and the green units. And you can see for each of these units a bar graph representing the probability that a voxel is part of that unit. You can see that the probability is high in the middle of a unit, and you can see that the probability drops towards the base of a unit and also drops towards the top of the unit. And then to the right-hand side, we see again the entropy, but now calculating for stratigraphical units rather than for lithological classes. And in the same way as with the lithological classes, if you look at the middle of the brown unit, you can see that there are three possible outcomes: the brown unit itself, the yellow unit, and the green unit. And because we have now three possible outcomes, the entropy or the model uncertainty of stratigraphy is rather high in this area. And the probability that a voxel belongs to a stratigraphical unit is derived from the uncertainties that we have calculated for the stratigraphical layers. So the regional uncertainty and the data proximity uncertainty lead us to an estimate of the probability that a voxel belongs to a certain stratigraphical unit. So in 3D it looks like this. This is the probability that a voxel belongs to unit C at the top of this part of the GeoTop model. And you can see that the probability is high within the unit and lower at its top and bottom. And we can do that for unit D and also for unit E. But then again, we have three different plots that tells us something about model uncertainty. And using the entropy rules, we then arrive at a single plot showing the model uncertainty in the voxel model with high model uncertainties so high certainties, I must say, in the middle of the units and lower certainties in the near the top and the bottom of the units. So we've done that for the entire GeoTop model, and we've delivered that on our web portal, so users can see in a cross section the stratigraphical units and the associated model uncertainty of the stratigraphy, and they can also look at the lithological class, so the most likely lithological class predicted by the model, and the associated model uncertainty. And that is the end of my talk. Thank you very much.
Thank you very much. This is great. And it's great to know how you can combine all this kind of, in a rigorous way, all this kinds of uncertainties. Do you have...
я уже за компом, ну, буду там ще в одне місце збираюсь, поки семінар слухаю по програмі.
Could you please mute yourself? You are not talking to everybody. Thank you. Are there any questions to you? Please raise your hand or unmute yourself or put your question in the chat if you like. Okay, there is a question. Okay, Nicola.
Hi, Jan.
Hi.
Thanks for the presentation. I was wondering, do you take into account the probability of a voxel belonging to one layer or another when you are drawing the lithological classes later?
No, in our modeling procedure, these are independent. So when we are modeling lithology, we regard the stratigraphical layer model as the truth. That would be a very nice next step to use uncertain stratigraphical layer models as input for the lithological modeling. Yes.
Thanks.
There are also other limitations. For instance, the lateral extent of the stratigraphical units is also something that is predefined, and we do not add any uncertainty to that. And the location of faults is also something that is, well, we accept it as being the truth. There's no uncertainty attached to that. So these are two, I think, two important steps to model uncertainty, but we're not there yet.
Okay, there are questions in the chat. There's a question from Anika. How much does this kind of model take geometry of the units into account? For example, if I have only one drilling of esker, gravel, but I know that esker should continue. So would I again need dummies to fill the gaps of knowledge?
Yeah. Yeah, if we have a gap of knowledge, or at least if the data doesn't support our knowledge, if we know more than what the data provides, like your example with an esker that you know by any, I don't know how you would know then that it's an esker that should continue, but let's say that you do know, that, yeah, then you have to put in additional data. So data points that are dummies, you call them, yeah. So we put a lot of geological knowledge into our modeling procedure, basically. I always present it as there's a lot of data and we interpolate and then the model is ready. Well, that is never the case. We always have to put in additional steering points or map data or whatever to make a model that is geological plausible. And that geological knowledge also is not attached with, doesn't come with an uncertainty.
Okay.
And Steve Tyson asked the facies probabilities is come from SIS. Yeah, that's correct. Sequential indicator simulation. Yeah.
And there is another one from Charlie. Why using a linear scale to classify entropy instead of logarithmic scale?
Well, I haven't tried that, so maybe I should. Why do you think that is a good idea?
Charlie?
Yes, it's because when you have a logarithm of 2, for example, it means that you have two equiprobable domains. When it's a logarithm of 3, it means that we have 3 equiprobable domains. So it's more interpretable to have a logarithm scale instead of a linear scale.
Yes, I could try that. I don't know.
Thank you.
Okay, and I see that Steve is raising his hand, and I think this will be the last question. Steve,
yeah, so it's just that with sequential indicator simulation, it doesn't preserve the any knowledge about the order of the different facies and how they may fit together. Whereas if you use the compositional geostatistics approach, then the cross variance between the different categories in the compositional model would be preserved. So I think that might represent a better approach than sequential indicator simulation.
Okay. Well, I can look into that. Thank you. Yeah.
Great. Thank you very much for your questions and answers. It's very informative, and we can proceed to the next presentation by Ingelise Møller and colleagues from the Geological Survey of Denmark and Greenland. And Ingelise will tell us about uncertainties in 3D geological modeling in the GEUS perspective.
And good morning, everyone. First of all, I would like to acknowledge my co-authors, Anne-Sophie Høyer, Rasmus Madsen, and Peter Sandersen for their considerable contributions for this work. In the 3D Geological Modeling group at the Geological Survey, we are working on methodologies assessing uncertainties in 3D geological modeling. We build on experiences gained from about 25 years of geological modeling in Denmark. The main target has been the mapping of the groundwater resources, and therefore the target depths have been around the upper 300 meters of the ground. Our learnings are general and fundamental and can be transferred to every kind of application. Communicating the model uncertainties, mainly to the scientists and also the authorities, have been a focus all through the years. Our experiences are obtained handling uncertainties in geological modeling in the Danish groundwater mapping. It started with qualitative uncertainty assessments for layer models and voxel models. Then different statistical methods like multi-point statistics were applied, conveying data uncertainties into model ensemble uncertainties. Lately, we have worked on methods honoring quantified interpretation uncertainties in layer models. Based on these studies and other work, Høyer et al. 2024 reviewed uncertainties all through the geological modeling workflow illustrated in this diagram. Uncertainties are introduced in every step of the workflow and is related to different activities and choices. It forms a chain of uncertainties linking aspects to all steps of the geological workflow. To outline my presentation, the most important sources of uncertainties are presented in the forthcoming slides, and I'll show you some examples of how the geological model uncertainty assessment can be communicated. First, we will look at the data evaluation and data collection phase, with focus on sources of uncertainty and limitations related to the modeling. Among what we call direct data, borehole lithological log are the most common, and among the indirect data, the geophysical information from electromagnetic methods often covers the major part of the modeling areas when we set up models in Denmark. In the next slides, we present two of the most important data types for some the sources of uncertainty and limitations, and it will be illustrated that it's important for these in the communication of the uncertainties. When you look for borehole lithological logs in Denmark, you go to the National Borehole Database Jupiter, which contains more than 450,000 boreholes, with about 250 boreholes with lithological information. These boreholes originate from a number of different applications, and for instance, and therefore the quality and the uncertainty of the borehole data varies. For instance, drilling methods in show detail. I just lost the drilling methods have a large variation in the quality of the geological sample. So on top of this, also there are large variations in the details of the sample descriptions, and that can be desperate that it's on the same sample quality. So there is knowledge needed for about the borehole methods, but it's also important that to communicate the data uncertainties. And it's also important to know in which way that the data have been stored in the database, because that's quite inhomogeneous. When we look at the sources of uncertainties and limitations related to the modeling of the resistivity, which is primarily obtained from the transient electromagnetic methods, it's important to have in mind that we have ambiguous data and that the resolution is different from the top to the bottom of the profiles. And it's also that we have ambiguity in the resistivity lithology relations, and also in relation to the iron content and concentration of the pore water, which influence directly on the resistivity. Furthermore, we have to be aware of the presence of corrupted and noisy data, and that because we use 1D inversion of the data, that we also have to be aware of that we have 3D effects in the 1D inversion models. So all in all, knowledge about the methods are important when assessing and communicating the uncertainties for the geophysical data. When it comes to the geological modeling phase, the first step is creating the conceptual model, and a number of choices have to impact on that. We take an example first here of two conceptual models. It has a different modeling purpose and the level of ambition, and thereby also that it will give a different number of layers in the conceptual model, and that will influence on the model scale as well. Another part of the setting up the conceptual model is that it could be necessary to revise the previous concept. That in this case you see here, that after gaining new data and a revisit of the existing data, it led to a higher level of geological complexity and intensive faulting in specific areas was observed. When we do uncertainty assessment of a model, it has to be done under the assumption that the conceptual model is the best possible. Therefore, it's important that the conceptual model is included in the communication of the model uncertainty. That the next two steps in the geological modeling phase involve choosing the type of modeling and constructing the model and assessing the uncertainties. When it comes to different types of models, it can be interpretation-based modeling, driven by a combination of prior data and the prior knowledge and the data. It's a manual modeling process, and the uncertainty assessment would be qualitative. Another type is the geostatistical models, which is mainly data-driven, but could also include prior information. It's a result of numerical calculations or simulations with a quantitative uncertainty assessment. More modeling types and approaches can be applied in individual parts of the same model, and that, of course, then the uncertainty assessment would be dependent on which modeling approach that have been taken. In the next slides, we'll show some examples on how the model uncertainties can be visually communicated. When it comes to the interpretation-based modeling with a quantitative uncertainty assessment, it can be evaluated for the whole model along the profile and shown as on a map. Or it can be evaluated at the individual interpretation points given by the model under the modeling process. Or it can be evaluated at the at each voxel in a voxel grid. The uncertainties are divided into uncertainty categories, which is based on the amount of data, the data type, the quality of the data, if the data are ambiguous, and the complexity of the conceptual model. This qualitative uncertainty assessment that reflects the geologist's own evaluation of the liability of the model interpretation along the profile. The assessment is relative to the model area, and it cannot be directly comparable to other models. In the geostatistical modeling approach using numerical modeling and simulation, the model uncertainties can be calculated or estimated through simulation. Quantitative uncertainties on, for instance, from geophysical data can be directly used, but there's also a need for quantifying subjective elements like the geological description from boreholes. Geostatistical simulation of the layer surfaces within error bars is carried out as a result of a number of model and result in a number of model realizations. An evaluation of the model ensemble gives the model uncertainty, and it can also be shown as the entropy. If you just zoom in, we can see that you can communicate the uncertainty by showing different realizations. But as Jan just showed, the entropy is a way of communicating the uncertainty in one plot, and here it's then the mode model that is faded by the entropy, and in this case, it's the entropy at the layer boundaries that is, and not the you can say, and not the layer itself that are calculated. And to sum up here, that the quantitative model uncertainty can be conveyed by the ensemble of the models. So, and now for the summary of this presentation. The uncertainty of a geological model adds up from a large number of choices in the geological modeling workflow. It's important to identify or prioritize the uncertainties in the workflow. It's impossible to make a complete quantification of the uncertainties in a geological model. The geological uncertainties can be evaluated and conveyed to subsequent modeling, like the hydrological flow modeling, through geostatistical methods. And the uncertainty is related to a concrete type of uncertainty. For instance, the uncertainty of the location of the layer surfaces in a layer model based on a specific conceptual model. All these aspects are important when communicating uncertainties in the geological modeling. Thank you for your attention.
Thank you very much, Ingelise. Very nice presentation and very informative as well. Are there any questions? If there are no questions yet, I would like to ask you, you were talking about different kinds of models, like interpretative models and geostatistical models, and different ways to calculate uncertainties in them. What actually works the best for you? Or is it that in some cases, and what cases, one approach is preferable to the other?
You can say if you do the manual interpretation, then you have to, you can say, do a subjective estimate of what you think, what is the certainty of the point that you put. But of course, you try to quantify these as well. So we are actually, for this, we have made a method where from the geologist's assessment of the uncertainties, we have tried to quantify that to be able to simulate the uncertainty of the layer of the layer model. It's difficult to say what worked the best for us. We have tried different things out, and we also tried that we have models where the geologists have estimated the uncertainties, and then from that we have tried to quantify them for the simulation. But we have done it as well on a national scale, where we don't have the geologists' interpretation of their interpretation points, and as I said, they will also vary from geologist to geologist how they do that. And there we have tried from, you can say, the amount of data that we have, the complexity of the area and so on, try to estimate or to quantify the uncertainties for this layer model simulation.
But then by geologists, this is quantification like high, low, or how do you quantify this actually?
You can say that geologists, would try to quantify, but also say, well, is this, when I put this interpretation point in the model, if it's based that you have a borehole with a high quality, you would say this is my best, my best quality of for this interpretation point. If you have some data that say that some boreholes that are not as good quality, but still it could be the next then level of you can say on the for the uncertainty of the interpretation point. And also if you have ambiguous data, or that you have no data, but you need that you conceptually know that it should go from a lower to a higher level for this layer, then you put in an interpretation point. And then, of course, that will be the lowest certainty of the interpretation point. So in that way, it's always for the geologist based on some rules from the data, you could say.
And some kind of uncertainty classes after all.
Yeah, then it would be uncertainty classes.
Okay, great. Thank you so much. I can see no other questions, so I think we could move, and it's actually time to move to, oh wait, there was something. We have a question, maybe we could still use 30 seconds for that. Uncertainty quantification is under valid assumptions that the conceptual model reflects the best possible model. Do you distinguish the conceptual model from the interpretational model?
Yes, we do. We start out the modeling process by going through, you can say, literature, the data that's already there, and so on, and to put up, you can say, a sketch of a model. Which layers should we have? What is the stratigraphy in this area? What kind of structures do we have? Is now in Denmark, which is a glacial area, that do we have an area with glacial tectonics, or is there buried valleys and so on? Looking at all what kinds of aspects can we have in the model area, Then we draw something like a profile, sketching which type of geology we would think that we find in this. So that's the conceptual model. And then we start doing the interpretation model. So the conceptual model is a sketch of what we see and what we expect and what complexity we will have in the area. And then the interpretation model is, then you can say the rules you apply as a geologist then is formed by the conceptual model. If you know that you are in an area with buried valleys, you will of course look in your data that other buried valleys, and then you will. So that's you can say the way that we work with a conceptual model versus the interpretation model.
Okay, great. Thank you very much. We need to move to the Mentimeter exercise, and this will be led by Daniel Markov from Geological Surveys. Please, Daniel.
Yes, good morning. Thank you, Eva. I will now share my screen. Let me know if you can see it, please.
Yes, we do.
Okay.
No, okay.
Okay,
Yeah,
so we will now start
presentation.
thank you. We will now start the third Mentimeter session, which focuses this time on geological survey organizations and case studies. And I will be guiding you through the questions. Before we begin, just a quick reminder to join and start answering the question. Please go to menti.com and enter the code shown on the screen. Or you can also use the QR code to start answering the question. Once you are connected, please tap next to start answering the questions. You can also answer at your own pace. There is no need to wait for me to move from one question to the next. And today, the next 5 questions are the same across all sessions. If you are attending multiple sessions like yesterday and today, only your first response will be recorded. We are also, a quick reminder that we are also asking the same introductory questions in all sessions in order to build a global view of the workshop. So new answers will add to the previous ones. And last reminder, if you have already replied to the first 5 questions earlier today, or yesterday, sorry, you can simply tap next until you reach the question specific to session number 3. So we would like to get to know you a bit better. So that's why the first question is about from which country are you joining us today? And we can still see the answers from yesterday. And probably some of you will respond today as well. We can see that we have a lot of participants from different European countries. And we have a strong participation from Germany, France, from the Netherlands. So yeah, participants from many different countries today. Now let's look at your professional background. So we still see that the research and technical sector is dominant, with 88% of the participants coming from this sector. Along with that, we have 2% coming from industry sector, 8% from institutions, and 2% from other sector. Let's now see how you are familiar with uncertainty in geology. So as we can see on the screen that we have 30 people that shows that they have an advanced level. 35 is dominant with an intermediate level of familiarity with uncertainty in geology. 28 basic and 12 beginner. Let's now see your expectation for this workshop. So what are you hoping to gain from this workshop? And we can see that there is a strong interest in exploring methods and tools to manage uncertainty, and also a strong interest in learning from case studies across topics and countries. And then some of you are interested in understanding the sources of uncertainty in 3D geomodels and maps. And few others chose communicating uncertainty as an expectation from the webinar or the workshop. If you selected other, we can see that some of you had other suggestions. For example, some of you said, looking forward to learn the latest developments, open source tools, practical skills comes twice. Some of you asked why uncertainties are so important. Learn recent advances in uncertainty in geomodeling. And others said, I hope for a fruitful exchange on uncertainty modeling. We will now move to the questions that relate specifically to this session. First question is about which scientific field handles uncertainty well and could be a source of inspiration for geoscience. And that here on the screen, we can see that physics has a big portion from your answers, as well as statistics, meteorology, geostatistics, weather, or also weather forecast. So we can also see that we have a wide range of responses. Moving now to the next question regarding the implementation within your organization. So to what extent are the following implemented in your organization? So we can see that addressing uncertainties in geological models are moderately implemented. Using external tools to manage uncertainties in geological models comes with a lower scale. And finally, developing in-house solutions to manage uncertainties in geological models comes first with 2.8. Moving now to the next question that is related to encountered situations. So how often have you encountered the following situations? So for the additional costs due to insufficient information are reported quite frequently. Then clients incorporated uncertainties from 3D models, geological models into their decision making with 2.3 that are not often present. And then finally, we have that uncertainty is discussed more for 3D models than for 2D maps are frequently encountered. So thank you for your answers in this session. I'm sure that these responses provide some valuable insights regarding the practices and some real experiences. So I will now stop sharing my screen and give the floor back to Eva.
Thank you very much, Daniel. We will use your answers for the discussion at the end of the session. It's very informative. And now we still have one presentation before the break. This is by Sirelda Bele from Albanian Geological Survey, and she will speak about exploring, quantifying, and communicating uncertainties in geological models. So, Sirelda, the floor is yours. Please share your screen, unmute yourself, and go on.
Okay.
Okay, everyone again. I'm Sirelda, and I'm represent the Albanian Geological Survey. Today I will present some of the main challenges we face in geological modeling and in handling uncertainties in geological maps and geological models. We can go in the next slide, please. The Albanian Geological Survey operates in the field of geoscience according to the law number 111 of 2015. Our institution acts as a technical and scientific advisor to the state in the field of geosciences and operates under the Ministry of Infrastructure and Energy. The institution has a long history. It was founded in 1922. When the Geological Office was established by Czech-Austrian geologist Ernest Novak. Today, after the more than 100 years of activity, it remains the oldest institution in Albania working in the field of geoscience. Next, okay, thank you. The Directorate of Geoinformatization is responsible for producing geological maps of different scales and managing a digital documentation on the Albanian Geological Survey. The department creates, updates, manages a geological database, processes geological digitally and georeference and digitized maps. It also develops GIS application and supports projects by linking special data with geological information. Is the main department here in Albanian Geological Survey. Next, please. Here is a slide who representing all the work that we doing in Albanian Geological Survey by our department. Well, as you see, it's with a director. The main task of the directorate includes three case areas. First is 3D geological modeling, which allows us to represent geological structure and or deposit in 3 dimensions. Second is GIS applications, which are essential for spatial data management analysis. Third, we build and maintain database for all the projects that we carry on in Albanian Geological Survey, which store geological information and make it accessible for analysis and decision making. All the projects, all database, or they will be archived in our archive digitalis or in the main archive of Geological Survey. Next, please. Here is an overview of geological maps in Albanian Geological Survey of Albania. In recent years, geological mapping and modeling in Albania have developed significantly. One of our main achievements is the completion of geological maps of Albania in a scale of 200,000, and 50,000, which now cover the entire territory of a country. Another important produce is the hydrogeological maps, mineral resource maps, and geological maps. We have covered in the scale 200,000 and in the scale 50,000 and in 20,000. many other topics or thematic maps that we covered, but this is the main maps that we represent here for you. Another important the third. Our department has just started on geomodeling of our body deposit. We have taken some of our deposit of chromite to approach a methodology on 3D modeling. You can go on another. Here is the map. I represent here the most important map of Albania. It is a geological map of Albania in 200,000 and hydrogeological map of Albania. Also, AGS completed 100 of the geological maps in the scale of 15,000 scale. As you see here. Another slide, please. I don't know if it's... Here is the example of 3D modeling. Our department has recently started working on 3D geological modeling, particularly for ore deposits. As a first step, we selected several chromite deposits in order to test and develop a methodology for 3D modeling. One example is the geological modeling in Vlahan ore deposit in Albania, which allows us to better understanding the geometry and distribution of mineralization. Here is the one methodology that we achieved in our institution. It's like we gather historical data, we make interpretation of them, create or digitize all the maps and the profile of the deposit. And later we go on the creation of the 3D modeling of ore deposit and on the chromite deposit. And later we go in the interpretation of the result of this production. And this example allows us to better understand all this 3D modeling example and distribution of the mineralization if we want to go in another ore deposit or to continue in another deposit like copper or another one. The next, please. One of the main challenges in geological modeling is dealing with uncertainties in geological data and interpretation. In many cases, we rely mainly in historical data and collected from previous geological studies. We have a long time that we have a very limited collection of new data on mineral resources, especially from boreholes. As a result, we often lack sufficient data to build detailed 3D modeling of stratigraphy, geology of the karst aquifers. This is the main reason for this is the lack of funding. Additionally, we are limited to using outdated software or open source tools, which restricted our ability to adapt new technological approach. Next, please. Another problem for us is stakeholder communication and interaction. Communicating uncertainties to stakeholders is also a challenge for us. Decision makers often prefer simple and clear answer, while geological data is often complex and uncertain. One effective approach is using visual tools such as map and graph, which help explain uncertainties in a more understandable way. No collaborative service request. We produce high-quality maps and data for their use, but a collaborative service would enhance value, but stakeholders currently prefer ready-made outputs processed by their own technical staff. Another one, please. Our institution also faces several internal limitations. The most important one is is a lack of sufficient funding to carry out all the necessary work, such as new drilling or extended data collection. Additionally, there is a strong need for training, especially of staff, especially in modern GIS and 3D modeling technology. Next. Conclusion, key recommendation. In conclusion, uncertainties in geological models and map mainly arise from limited data, complex geological conditions, and outdated tools. To address these challenges, several steps are recommended. First, investment in modern geological survey technology. Second, training staff in advanced GIS and 3D modeling software. Third, improving communication methods with stakeholders through simplified visual representation. And this is for finally the second. Thank you for your attention. I don't know, it's a good hearing with all of this technical problem.
Thank you, Sirelda. Yes, we could hear you fine. Are there any questions?
Yes, please.
Yeah, I have a comment and a question for Sirelda. Thank you for your presentation. It is very interesting to have a description of your approach regarding 3D geomodeling and the uncertainties. It's also very interesting that you consider maps, I would say, at the same level than 3D geological models regarding uncertainties. It was one of the questions of the mentee, and we not always, but very often have questions regarding uncertainties on 3D modeling, but very much less regarding maps. There is also something you said regarding the requests from the stakeholders. You said that they don't really request for uncertainties, but they request for a model or a map that is as much as possible close to the reality. In fact, is it the case?
I understand the question. Can I go on?
Yes, please.
Yeah, I mean, you said that the stakeholders, in fact,
Yes.
You said that they don't ask for uncertainties, and they ask for just one solution. In fact, is it often the case? Always the case?
Yes, by our law, the stakeholders, they just buy our producing, like maps or study, and that's all for that. Even they do study from their own, they don't give or they don't bring the data they get or gather and to bring here in our institution to collect it or to archive in our archive of Albanian Geological Survey. Or if they buy a map, it's simply map. It's no matter the thematic of map. They prefer to work by their staff, and they have the group, and if they want to do the database, if they want to do 3D modeling, it's no matter what is the case, is or deposit or water or whatever, they do it by themselves, and they don't ask for how it's the map here, or if they have questions, they don't do it. They just they buy the standard map we provide it for us. We don't collaborate just to start a project or a study and to take advantage from our part, and they will take the advantage for our. They can take data, and we can take new data, for example. That it will be very good for us. I don't know if I was
yeah, thank you. Okay.
Question.
Any other question to Sirelda?
Yes.
So if I may ask something, the stakeholders that use your data or your maps, these are mainly like mineral companies, like mining sector, and is it many different, let's say, mining sector companies, or it's like one big state-owned company? How does it work? I mean, would you have if you started cooperating with your stakeholders, would it be many different stakeholders or two major ones, let's say? What's the structure in Albania?
If we collaborate with the stakeholder, will be the different. For example, in the sector mining, there are different private company that operate in different mineral in different mine. They get the permission and they work in different company, different ways.
Okay. And they don't later share the data with you? So
no,
where's your data coming
they
from?
just get permission from us, and they have mandatory to bring just a study.
Okay. Mm-hmm.
For in Albanian Geological Survey, they buy the first data or primary data, and then they used to buy their staff. They work by all the data they work or prepare from their staff, and we don't have the other data they can gather, and we don't have it their data later.
I see. After they finish the project, they don't share data.
Yes. No, just in the study. The study they can share, but there are no data because they're drilling there. They have the new data. They have boreholes, and it will be a good thing to collaborate in this way.
Okay.
I don't know.
Are there any other questions? Okay, if there are no more questions, I think we can have a break scheduled in for our meeting now, and we reconvene here at 10:40 sharp, please.
Thank you.
Thank you very much. We are back after the break. And now we will see two case studies, and we will have a chance to look at two presentations. First one is by Jasper Mars and colleagues and from the Netherlands. The title is Causes of Uncertainties in Geomodeling Inputs, Data Review of Paleozoic Geology in South Limburg-Euregion, Meuse-Rhine.
Hi everyone, welcome to my presentation titled The Causes of Uncertainty in Geomodeling Inputs. For those of you who don't know me, I saw there's a lot of people watching, so probably a lot. I am the PhD student of Hemmo Abels from TU Delft. And I work closely together with Alexander Hube and Geert-Jan Vis. My name is Jasper Mars. The results I'm going to present to you in this presentation are the first results of the first study of my PhD project. And it has as a central theme in my PhD project is geological uncertainty. And the uncertainties that we identified here, they were done by me from a geological perspective and from all the co-authors, and they are all geologists. So maybe sometimes the language or the perception will not be completely the same as the geomodelers. But anyway, I think that they might still be of interest to prevent this knowledge gap that might exist in the uncertainty analysis. And this examination of uncertainty was done through a data review of Paleozoic geology in the Euregion Meuse-Rhine. That's a region located at the triple junction between the Netherlands and Belgium and Germany. And important for my Dutch colleagues in TNO to realize about this region is that the Paleozoic geology is completely different than most of the geology elsewhere in the Dutch subsurface. So the rocks, they have been buried deeply, they are fractured and very hard and competent. They are chemically altered, they often have a high degree of diagenesis. And then they are also contorted in one of the biggest mountain building events to have occurred in Earth's history, that's the Variscan orogeny. And the frontal tip of that huge mountain chain runs exactly through this region. So you can imagine what happens to a horizontal layer if it's situated in this mountain belt. It's not longer horizontal anymore. And another disclaimer is that we did not include seismic data in this review. That was not within our scope, and it's already been done. And also, we are more on the explicit side of the modeling spectrum. So what we assessed and examined are more geological maps, cross sections, stratigraphic borehole profiles, those kind of geomodeling inputs. Right, so let's look at a map of this region. It's situated in South Limburg in the Netherlands, at this triple junction between these three countries, Belgium, Netherlands, and Germany. And this region has recently been of interest for a big science project called the Einstein Telescope. And for this project, the Einstein Telescope, also a geological subsurface investigation, a site investigation is conducted, for which boreholes are being drilled and have been drilled. And these new boreholes, they included cores. They really gave us an opportunity because now we have new data to work with, and we can process the data, we can interpret the data, and we can track the uncertainties that we encountered while doing that. And then in the end, when we have the stratigraphic profiles of those new data, we can use them to compare them with the existing data and materials as a sort of validation check to see if there are mismatches which would demonstrate the uncertainty. So that's what we did, analyze new data and compiled a lot of data, and then try to find if there are inconsistencies mutually within the data or the interpreted data. This is how the borehole dataset looks like. These are all filtered from the Paleozoic, so all the younger rocks, they are not included. And they are compiled from 5 different geodatabase viewers from the 3 countries. And I put a box around the 3 newer boreholes that have been drilled for this Einstein telescope. But the data set, it also looks sometimes more like this. So these are physical, tangible objects. And this includes sometimes more concepts and interpretations. Sometimes it is in this geological map, such as the one in the white box. It's the unfolded geologic map of the region, which is also the most recent geological map of that region. And this is the map that we try to assess with the newer data. And also borehole reports, such as the other one in the white box, original description, sometimes handwritten, about what has been described with for legacy boreholes. Right, so now let's look at what happens when we compare these data. On the left, there is the new borehole, one of the Einstein boreholes, and we described it for its lithofacius to interpret the stratigraphy, and we have combined that with a biostratigraphic analysis, looking at the small fossils inside the rock to see what age it is. And we found these gray-colored, mica-rich fine sandstones, and they are of Devonian age. Now, interestingly, on only 250 meters apart from that new borehole, there was a borehole drilled in almost 100 years ago in 1930. And that borehole also described at a similar depth the same type of rocks, gray-colored, mica-rich sandstones. But they, with the knowledge they had 100 years ago, they allocated that rock succession to the Carboniferous. So that's 300 million years younger. And now we know with the new rock and the new knowledge that has been gained that it is probably also Devonian. However, on the geodatabase viewer, so NLOG in this case, it is based on the original borehole report in this case. So it still says Carboniferous for that borehole. And that is one of the data inconsistencies that that demonstrated the uncertainty that the geologist was met with 100 years ago. So now let's look at the geological map that I showed earlier. Here's a digital version. It has been, the layout has been adjusted in GIS, and we plotted all those boreholes with the stratigraphy with colors on top of the geologic maps. And then in the places where the colors do not match, I put circles around it. And those are the stratigraphic mismatches between the geological map and the compiled borehole. And mostly they are close to their bounding surfaces, which would not necessarily indicate a high degree of uncertainty, but sometimes, for example, there is one blue one in the right of the map, which is in the middle of this yellow polygon, which indicates more curious, maybe more uncertainty. And then there is also a geologic map that's in figure B that appended this geological map. And here we plotted the same borehole that I presented in the previous slide. And we plotted on top of this cross-section. And what we then see, you see it with the black arrow that indicates this borehole, is that you have yellow, and then at 50 meters, you already have the red. Well, the cross-section indicates that the red is at 2 kilometers depth. So there is quite a large depth mismatch between the stratigraphic units there, and the blue that has been indicated appears to not exist at that location. There's an unconformity that the geologists previously didn't know of. And if we look at a different cross-section from a different geologic map, we see a similar pattern arise where you have a borehole which has blue up to 800 meters indicated by this other black arrow, while the red is already indicated below the blue around 100 meters depth. So there are these mismatches indicate that these geologists have to deal with uncertainty, and it's easy for us now to look at this map and have compiled all this data and think that they did a sloppy job or that it's all subjective or something like that. But this is not a critique. This is simply the uncertainty that with the knowledge the geologist had and the objective criteria he uses for his interpretation that he has to deal with. So that's important to remember when we look back at these kind of materials. So there's actually many more instances where we found data inconsistencies and also different sources for how this came about. And we put it in all these bubbles. I don't have time to go through all of them. But I wanted to show that there is numerous sources, and also with this line, I wanted to show that they are interconnected. And sometimes also different categories influence each other. So this makes it quite a complex dynamic to understand, fully grasp the uncertainty in the geological processing or geological interpretation. Anyway, we try to categorize them in 4 groups. And in yellow, that's one of the cases that is interpreting faults. First, you have to recognize the fault. And then secondly, you have to interpret the scale of the fault. Does it have an offset of 10 meters? Or does it have an offset of 100 kilometers or 10 kilometers? Sometimes it's not possible to distinguish even that. There are objective criteria that you can use to make an estimation, but it's simply not possible to be sure without seismics. Then there is another category that's transferring data. So that's mostly related to the geodatabase viewers. They are, for the most part, correct by far. But still, what we saw is that in some occasions, there were boreholes that have an original description of which the geodatabase is based upon. And then with later re-evaluation, because more data was added, more analysis was done, there was a reinterpretation of the stratigraphy. And then that reinterpretation has not been included in the geodatabase viewers. And then there is, as we have shown with these mismatches earlier, uncertainty in legacy materials. And this, of course, stems from decisions that you have to make to complete the product, to complete the geologic map. And one important one is the stratigraphic interpretation. Sometimes there is multiple valid interpretations of which stratigraphic unit the rock actually is. And this mostly relate to what I call an ambiguous facies. Here is an example of that. So on the left-hand side, you see what is called a Namurian shale. It's upper Carboniferous. And on the right, you see an Dimension, so that's lower Carboniferous limestone. But they very much resemble each other. It may not be the best example because the left one is a bit more clay. But what happened is that the limestone was completely weathered and silicified, and it lost all its carbonate. And therefore it became unintuitively very similar to Namurian shales. And in the past, what has been shown is that they were interpreted as Namurian, and only with additional information from petrographic analysis and biostratigraphy, they found out that they were actually Dimension. So that's one of the problems that geologists have to face. Right. So what I showed is that there are several sources of uncertainty. But what now? I think it's important, and that will also show is a sort of necessity of validating legacy materials before you embark on the geomodeling exercise. In a way, input uncertainty may be the product of the frequency of certain inconsistency or frequency of certain uncertainties and the degree of its inconsistency or the uncertainty. And somehow we have to weigh that, because an uncertainty or an inconsistency can frequently occur, but if it doesn't impact model design or the way you make your framework model, then does it really matter? So the degree of inconsistency and weighing those is that's a challenge, and that's where I think progress could be made. Anyway, important for a geomodeler before he starts to work with legacy materials, for example, is to ask and have a discussion with the geologist and ask him how frequent do certain inconsistencies occur and which type of uncertainty matters most, do you think? And also think about what the impact is on the model design. Right. So that was my presentation. I don't know at what time I am, but if you have any questions, then I'll be pleased to answer them.
Thank you very much. Great. Yes, we have time for questions. You are actually quite well on time. We have 3 minutes left. So any questions to Jasper? Guillaume, please.
Did you try to quantify it? Question
Hi, Jasper. Very nice presentation. Very challenging work, I think. So how do you plan to resolve this inconsistency at the end of the day when you will start to create the 3D model from this data? So spotting the inconsistencies is very important, and you did a great job there. But at the end of the day, what will be your approach to try to decide which data is correct and which is not? I mean, that's a very challenging problem. Do you plan to rely on expert knowledge? I mean, do that by hand, or do you plan to use any automatic method? And what are your plans there?
Yeah, so
I don't have an answer for that.
No, indeed, that's a sort of follow-up. Indeed, what is and the next step arising from finding the inconsistency is indeed the question how to deal with it. And one of the ways to deal with it, especially what modelers like, is to quantify it so you can actually calculate with these uncertainties. And one of the big challenge there is that a lot of uncertainties. So what we see, there's different types of uncertainties, and some of them they are categorical. So they are not quantitative, they are qualitative. And to make a step from a qualitative uncertainty, for example, we saw in one of the cross sections that there was the blue stratigraphic unit indicated, but it didn't exist at all. So that's a categorical uncertainty, which is, I think, very hard to express quantitatively. So I don't know if it's how this can be done. I know there is Bayesian frameworks that at least in part can solve this. But it's also an important step. I think this leads to the next session to not only quantify it, but simply also to communicate it and how to. But I don't know actually how the best way would be to quantify these uncertainties and to ultimately incorporate them in a modeling workflow.
Thank you. Thanks.
Thank you, Philippe.
No, this is just a comment on this discussion. What you are talking about, Jasper, it's what we call the inequalities constraint. This is the fact that, for instance, you know that you are in a given formation, but you have no point for that, or and you cannot take it into account directly. And the same thing when you are at the end of at the bottom of a borehole, you know that you are in such formation, but you don't know where is the real bottom of this formation. You just know the bottom of the borehole, in fact, and you cannot point exactly the where is the limit of this formation with the one that is below. So this, we call that inequalities. In fact, It was just my comment, and I think there is a question from Zbigniew in the chat.
Did you try to quantify it?
No, I did not. No, I think what should be interesting to quantify this is quantifying the frequency, for example, of inconsistency. And then also what might be interesting, more quantifiable, is we had these 4 categories of uncertainties in this case. And now one way to quantify might be, for example, the uncertainty in interpreting faults. And then with sensitivity test, what would be actually the impact quantitatively of interpreting faults differently on the outcomes of the eventual outcomes of your model. And I know also there is people presenting yesterday who are already working with those kind of tools and exploring them. But I did not.
Okay, so this is something to think about. I'm afraid we need to move to another presentation. There is another question in the chat, so well, feel free to respond directly in the chat. And there is also one question in the chat for previous presenter Sirelda, so if you would like to engage directly in the chat. And let's now listen to the next presentation, which is it's also a case study and also from the mountains, somewhat younger, I would say, because this is from the Alps. And the presenter is Ferdinando Musso Piantelli, and he and his colleagues are presenting a talk on identifying uncertainties in 3D geological modeling in alpine regions, challenges and open questions. And we can already see your presentation. Great, so the floor is yours.
Yeah, I tried to save some time already. Thank you so much for the kind introduction. Can you hear me also well?
Yes, perfect.
Perfect, that's great. So I keep on moving in the same direction of this morning's presentation by bringing you to the alpine regions in the core of Europe and discussing a bit together the modeling project that we are running in there with the challenges and open questions that we have in trying to identify and connect the uncertainties quantifications to the model that we are doing. So our survey with the National Geological Models program until 2030 have the mandate to cover the entire country with the large-scale geological models. And we plan to do that with three main geological modeling projects that are subdivided by the main tectonic, let's say, regions of Switzerland. So to the north, we have the Jura with the Jura 3D modeling projects you might have heard about. Then we have the Mittelland, the Molasse region here in light blue, where we already had the GeoMol modeling projects that is finished, but is continuously being updated as part of this program. And then to the south, all these nicely colorful units that are the alpine regions of Switzerland. And in there we have a dedicated project called Swiss Alps 3D running from 2024 until 2030. That is the object of the presentation of today. So in the Swiss Alps 3D project, we are targeting exactly this region that is quite large. We are talking about 60% of the country, so a very large modeling area. And we target the main lithostratigraphic and structural units of those alpine regions. As a project, it requires a large component of research. Our modeling partners are the universities listed here at the bottom of this slide. And together, they are all modeling, they are working separately in one of the regions. So we subdivided this large model area in 8 sub-modeling regions, and each of these teams is working independently in them. And then we will combine all these different separate models in one finalized Swiss Alps 3D model. So in the presentation of today, as we are still a bit in the early stage of the modeling phase in here, you might understand that we don't have yet a full perfect tool that allows us to quantify and connect uncertainties to the models that we are doing. So the idea that I had today for joining this workshop was to come to present the type of models that we do, the challenges that we are facing, a key example where you could see what we can do with the data that we have, and then raise some questions, hoping for some feedback from the audience, some ideas on the audience on how we could actually try to implement the wonderful tools I've seen yesterday, the theories I've seen yesterday, onto such a type of models that we are trying to build and deliver to the country of Switzerland. So to do that, I would like to give some more details on the models that we are building. And for doing that, I need to explain you a little bit the playground on which we are moving in. And the best way to access these is to discuss the challenges that we need to face when we plan such a modeling project. And you find them listed here, the main ones. If not, we want to mention the resources, the people, the number of people involved, and the time also that we have as frameworks, let's say, of this project. But you focus on the technical challenges that we have for this project. We have the first one is the scale. So we are talking about a very, very large modeling area, 60% of the country. And then as a second challenge, we have the complexity of the geological features that we are trying to model. As you can imagine, as alpine regions, we have multiple deformation phases for each of the units that we try to model. And as you have seen in the slide before, each of these modeling area presents its own characteristics, tectonic history, evolution, and therefore challenges to model. These two challenges very much influence the modeling approaches that we can use. So the scale, so the dimensions that we try to model, the large area that we try to model, as well as the complexity of the features that we would like to represent, limit the approaches that we can use to achieve such a model, to build such a models. Therefore, we are using now a combination of implicit approaches for a first version of our models, and then we need to refine them in a more explicit ways. And then the last and also maybe very large challenge that we have in this project is also visualized here in this slide, that is the lack of subsurface data. So mountainous regions, alpine regions means remote with less population living in those regions, and this is reflected in one-to-one in the subsurface data availability. And here you find the deep boreholes or the seismic lines available in Switzerland, and you see that where most of population is living, we have a large, quite good coverage of data of the subsurface, and in the alpine region we have areas with almost nothing in there. So this is the playground we are moving in, and in the next slides I'm trying to show you already some first results coming out of the modeling we are doing. So at the moment we are focusing in the western part of the Alps in Switzerland, and you can see actually what you can expect as a product of this modeling project. So a series of meshes, surfaces representing the main lithostratigraphic structural boundaries of these alpine regions. So yes, one version model, not multiple version models for this, trying to represent the geometries of the top, bottom, or the main structures of what you can see here, for example, of the West Penninic, the Helvetics, Prealps, Subalpine molars, all the type of lithostratigraphy, all the units that we have in the Alps. Sorry, I have a bit of background noise. Okay. So just to complete what I wanted to say on this slide is that what we are trying to do in this modeling project is basically for the first time to represent what we know and what we understand of the tectonic regions in this modeling area. So we are trying to, for the first time, to connect all the different interpretations that we have in there. So at the moment, in all these regions, we have nothing. So the subsurface you have seen is very sparsely covered by data. Nobody ever tried yet at this resolution to try to interpret it in a homogeneous way, in a complete way, and that's what we are trying to do. So that we are producing a framework model that then in the future people can zoom in when we have a more detailed case study in one or the other area in the region, and then dive in at a way deeper, precise scale, refining it and trying to understand. So we give a framework concept for future then applications. So now that you understood a little bit better in the playground we're moving in and which type of models we're building in, I would like to bring you in one of the areas where it seems that we have quite a good coverage of data and to show you what we can do there. But please remember also that there are other areas like these ones here where there is nothing. So keep also that in mind when we will discuss the whole model again at the end. So as I promised you, it is an alpine region, so we have really high elevations in there. We start at 600, we go up to 4,000-meter peaks. You might know actually this area as it had a very large glacial collapse with a very large also rockfall involved in there last in May a year ago. So you might have seen it in the news. It was a very big thing here. And also we have also a typical coverage of high mountainous regions, so very large glacier coverage, all the sort of quaternary in fields in the valley that prevent us also to see some geological information there. As you have seen before, we have a good coverage of data in here because we have a tunnel, a railway tunnel running through from north to south through the area that actually unravels for us a little bit the geology in there. So we have a series of crystalline units intruded by some granitic rocks. And this makes a dome here that is actually a massif, one of the external crystalline massifs of the Alps called R massif. And this is then overlaid by a series of nappes on top of sedimentary units that are very intensively deformed and placed on top of the crystalline units. So out of this region, we made a model in the same style as you have seen before, one version model. That's it. That's representing what we can see, what we can understand of the geology, our interpretation of the geology, in here representing the crystalline units, the sedimentary nappe here in blue lying on top of it. But on which actual hard geological information have we been building this model? So first of all, we have been using the tunnel information, one of the most precise information that we could access there. So basically where we could intercept the tectonic units, the boundaries, the structural informations that we wanted to use for building the model. Then all the boreholes drilled for prospection of these tunnel and for other things. And only few of them really intersected the units we wanted. Remember, we are modeling at a regional scale, so only few boundaries, few structures are relevant for these type of projects. And most of the boreholes, as we also said in the presentation before, are only saying an information we are within a certain unit or not in another one. So that's the key information we can get out of them. Then the most important information, it was a lot also discussed yesterday, and I really enjoyed the discussion on there. So the maps, the geological maps used as the input for a geological model, and you can see, having seen the slide before where I tried to show you the data, the geological maps is mainly our golden information for building models in these regions. So we have actually very good coverage of map in Switzerland due to the GeoCover and Atlas project. And there we have also all the type of problems were listed already yesterday. So different map sheets published in different years. So not always agreeing between each other, but for this project, we are actually building a harmonized map, going through all the map sheets for the contacts and the structures that we want to use. And we try also to assess a little bit the accuracy of these maps so far only in two different groups, but I would like to dive a little bit deeper also in that type of uncertainty quantification of the lines and therefore points of these maps and use them as the input then for the map. And also another thing I wanted to highlight that is for the Alpine regions a very important thing, and maybe for other regions a bit less. 2D geological maps, they're always named like this, but actually they have a lot of 3D information. And for the case of this region specific, you've seen that we move from 600 meters up to 4,000 meter peaks. And this allows us already a good chance of interpolating planes already for about 2 kilometers. And this is something we are very grateful for then extrapolating in the subsurface. Then another source of data we used to build this model were also seismic data. So we didn't have straight within the modeling area seismic profiles, but they are just outside. And we used then the published interpolating lines for the top of the crystalline units to have a better guess on how the dome of crystalline units is dipping to the north, to the west, and to the south, so that we could have a better guess. So out of this hard geological information, we have been building this model. And this brings me already to the first set of questions that I prepared for the audience, trying to collect some feedbacks out of you by what we have seen until now, what are we targeting with this project, what I showed you now in this small key study or example. And basically are already what I said in the introduction. So how do you think that the tools we have seen yesterday, the theory we have seen yesterday, could apply to such a scenario? So with a large-scale modeling project where we have a very complex geological setting and very few data available and very sparse also, so not homogeneously distributed. And this is the main question I have that could be then tailored and in more detailed question that is basically how from a geological information do we move away with the uncertainty? So if there is a universal relationship between distance and uncertainty, which would be very interesting for us to have a better insights in there. And then the last point I would like to make, and was already a bit mentioned by the slide, by the presentation of before, is that, yeah, of course, we used all these hard geological information, but we have also done a lot of soft information that were also very useful for building then this model. And these were a lot of cross-section, geological cross-section we we loaded in the area, and that we are also loading in the whole Alpine regions, that coming from published literature, from the geological maps that we have in there. And the problem of these data set, let's say, is that cannot be considered as hard fact, where we can pick an horizon and put it in our model, because they generally don't agree between each other. So they always focused in one or the other aspect they wanted to study or verify, and sometimes oversee other aspects. So what we did by building this specific key example, but also generally what we are trying to do with these scientific projects through the whole Alps, is to harmonize for once then all the interpretations in one version model, as we have discussed yesterday. And then the last point I would like to make, also very important again with these research projects, is that we are also trying to connect to the model that we're building a lot of validation approaches, as for example, cross-section restorations throughout our models, to validate our understanding of what we are trying to model. And here you see an example from the key study I was trying to show you now. That is, it was here actually, it was cut out of a much larger model of the entire massifs that we then retro-deformed in space and time to unravel a bit this structural evolution of the crystalline units, as well as the emplacement and then evolution of the naps on top of it, so that we could validate what we have been doing. And this brings me to the last slide of the presentation, where I try to raise two final questions to the list I had before. That is basically, how could we even also include this prior knowledge that we have, all very valuable in the areas that we are trying to model, in form of geological cross-section reports, any sort of soft information that could help us in building the model, and how could we quantify it or include it in the quantification that we do it. And then another actually interesting point to my perspective, there's with restoration, with any sort of project that we try to apply to the models, are also in a way reducing the uncertainties on the models we are building. However, it's very hard to quantify them and include them in our uncertainty. Many to be discussed in the few minutes remaining, but maybe interesting for the discussion before lunch. With that, I really thank you for listening and for the opportunity to present. Thanks.
Thank you very much, Ferdinando. This was a great presentation. I enjoyed it a lot. And you actually posed an inverse problem to us, because it's usually questions for the presenter, and you proposed questions for the audience. Still, are there any questions to the presenter from the audience? And then I think we can start the discussion part with your questions. It would be very nice introduction to the discussion.
made too many questions to the people, I think, and people are just overwhelmed. But I see a hand.
Guillaume is, yeah, I see Guillaume is, Go on, please.
Yeah, Ferdinando, great presentation and very challenging work. We worked on similar things in the Italian Alps with Andrea Bistacchi and Gloria Arienti a couple of years ago, and that's really challenging because this is really under constraint and characterizing this huge amount of deformation with limited data is really a challenge and needs a lot of concepts. So I understood. Can you tell us more about the methods you're using? I mean, this is mainly about cross-section, wireframing, and trying to associate things along some axial directions. Is this correct?
Yes, exactly. So it would be in some areas. So again, if I have to reply for the whole project, that's it. That's what we are doing. And then there are areas that is easier to model and areas that are a bit more complex. So in the easier ones, we try even with some more implicit techniques. So we try to make some version of a first NAP, for example, boundary, and then we need to refine it and bring it to the quality we need. So more in explicit way. So that's how we are doing it. But yeah, that's open to any input. And but so far it's like this. And one version. So this I tried to stress it during the presentation. So that's it. We propose that's the shape of the NAP and no other versions.
There was some really interesting work which didn't receive the credit it deserved, I think, by Jean-Pierre Gratier about 20 years ago, who was using the concept of developable surfaces. So he worked quite a bit on this, and I think this has somehow vanished, but I think probably we should reactivate that, because when you think about this, so you have a lot of semi-cylindrical structures, but quite often there's quite a lot of along strike variations as well, from what I understand. And back to your question about how we could use structural restoration to try to validate the structures and integrate that into the loop. I mean, this is something we have tried, but to be honest, we did not succeed to do anything meaningful. And I think the most promising type of approach would be to use some of the things that Jean-Pierre Gratier did. I'll try to find the reference.
Thanks,
and put it in the chat. But yeah, restoration is challenging. So just to finish, and I see that Philippe wants to talk as well. Restoration is challenging because it's also making assumptions, right? So vertical shear, blah blah. So you can integrate that into uncertainty quantification, but you also know that the area conservation and like if you're doing cross-section restoration, you assume there is no out-of-plane placement. So you really have to be careful with all these assumptions, because otherwise it may really reduce a lot the uncertainty, and that would not be a good approach. But yeah, Philippe, go ahead. Thank you. But great work.
Thank you.
You were talking about Jean-Pierre Gratier. I'm afraid it was in the late 90s. It's a long time ago. But you're right. We worked with him as well in the Alps for this kind of not restoration, but developing 3D surfaces we were constructing at that time. Yeah, thank you, Ferdinando, for your presentation. Even if we already discussed about that, I have no question, but just a comment. But you told about that. In fact, with the information you have on the map, you already have a 3D information, because it's in a way like a borehole, because you are very variation in the depths. So provided you can use a method that take into account both these limits on the geological map, of course projected on the topography, and if you can use also some dips, some orientation data, it's always easier to model the Alps, in fact, than very flat, very flat terrain with this kind of stuff.
True.
Yeah, well,
this is what you haven't talked. Sorry, you haven't talked about about deeps, geological deeps, and so on. Are you using them?
I simply forgot to mention it. It was also in the slide. We also use them. So of course we include everything we can. So if I would have more, I would include more. The problem is that there is really a limit on what we can access. That's a bit the major issue we have.
Okay, there was another question in the chat, actually similar or along the same lines of Guillaume was talking just a second ago, and this was about cross-section and larger scale data. Jan Franek asked if how much the validation through profile restoration lead to further improvement of the model.
So basically, when we did that, we readapted the model. So we learned some concepts on it, some structures that could not work that way, or some emplacement of the NAP that could not work this way. And this improved us in building actually the subsurface interpretation that we had in there. So we had a loop in there in improving the model. So that's why we did this validation approach. And so we could fix all the elements together. Yeah, so that's the best that we could do. I'm sure that there is even more better ways. The bigger problem I have is that once we have done these models, then they're very static. So it's very hard to update. If I get new information, it's very hard to connect uncertainties to that. So the validations are good to make the version we want, like we obtain at the end of the project. And then after that, then it becomes a bit hard to communicate to the people all the hard work behind, but as well also the limitations it has. And
just a very short question. What software do you use for? Because it's really complex structures. It's not straightforward.
So by working with universities, we, for all the different groups, so we at the survey, we are working with Move from PETEX, that is the one we use to manage all these modeling projects coming together in one version. But from universities, they are actually free to use different softwares. They are mainly using Move as well, but we are trying to use also GenPy, P0 from Andrea Bistacchi in Milano, that is based on loop structure, I think. And I even tried GoCAD a little bit. So we are open to anything, but mainly Move. So the model I showed you now on the slides was Move from PETEX.
Right. Okay. So maybe we could still come back to the Mentimeter results and think a little bit about what we saw in the first results, because this is quite interesting, I think. There was a question about inspiration from other fields of uncertainty calculation. And what came up were physics, geostatistics, but also various words related to weather forecasting, meteorology, weather, and so forth. So it looks like we, in this kind of work, or maybe this discipline has like had to think a lot about uncertainties, as we do, but they also have some solutions. Does anybody want to comment on this, on how can we use this work to answer, and to maybe it's a little bit also already touching on the next session about presentation of uncertainties, but I guess also about how to calculate them and how to think about them. Is this going to be envelopes, or how do we want to proceed with uncertainties? Anybody would like to comment on that? Yeah, Charlie? Charlie was first, I think. Charlie Kirkwood.
Okay, thanks. No, well, Guillaume should go as well. Yeah, well, on the weather forecasting and the meteorology, I was kind of pleased to see that came up quite strongly in that Mentimeter question. Yeah, well, I did do my PhD. I did it in partnership with the Met Office in the UK, which is our weather forecasting agency. So in that, I was able to learn, I guess, from them how they go about modeling uncertainty and also how they go about communicating it to people. And I think that there is a lot that we can learn from how it's done in meteorology. I mean, the uncertainty that they deal with isn't necessarily the same that we have. Well, I think it's actually basically everything that we have, but it's actually a little bit more because they also have this basically initial condition uncertainty. So they don't know how the weather is going to evolve through time, and how the weather does evolve through time is very dependent on the current state of the weather. So basically, they've got this whole temporal aspect that we generally don't worry about so much. So I guess our job is simpler in that respect, although geology, you could argue, is more complicated than, well, maybe the lithosphere is a bit more complicated than the atmosphere, but not drastically so. So I think, yeah, there's a lot we can learn from basically ensemble modeling, I think, which is basically how they go about it. And that's also how they then communicate the uncertainty, which is kind of summarizing these kind of ensemble results. So yeah, in weather forecasting, well, for the UK at least, since the year 2000, they have not been producing single models. Like everything has been ensemble forecasting. So that's 25 years they've been doing, yeah, these ensemble models. Anyway, I think I've been talking long enough, so someone else should say something, but I'm happy to say some more about that if people are interested too, because I guess I've got some insight from the inside.
Great.
Thanks.
Guillaume, would you like to comment?
Yeah, I completely agree with what you just said, Charlie. I think there's a lot of inspiration to be used, and actually it's being done quite a lot in hydrogeology and subsurface reservoirs, where there's been quite a lot of work with ensemble Kalman filters or ensemble Kalman smoothers, because one big difference between what happens in meteorology or ocean science for data assimilation and what we have in geosciences is that I mean, we may not have as much boundary condition uncertainties, although I still think we do have quite a bit of that, but we have a lot of static parameters, whereas in meteorology or oceanography, everything is dynamic. And I would tend to think they know the equations, I guess that down to the physical, down to some level, and we don't necessarily know the equations that characterize the geological medium. So I agree with you, Charlie. To some extent, we face a simpler problem, and to some other extent, we also face a more difficult problem. I also completely agree that in terms of mapping and displaying the uncertainty, there's probably quite a lot of sources of inspiration that we could use in those fields. And that's a major, probably a major area to look into.
Yeah, and in a sense of temporal data, well, hydrogeology would be probably the discipline where this would be more similar. Dmitry, you wanted to say something?
Yes, in terms of philosophy, yeah, I wanted to say that every uncertainty is a possibility in some way. Okay, so if we will look at them as on possibilities, unknown is a possibility to research it, to get to know more detailed its consistency. And of course, it's not uncertainty, it's a probability. So that's possibility with a probability. And as for our yesterday's talk, yeah, I've thought, so the most difficult will be modeling of isomorph substitutions. So chromite magnetite, yeah, for example, tantalite columbite. So when we in one deposit have minerals, yeah, with different chemical composition from zone to zone. So this is so microclinarta class, so polymorph substitutions. So the same chemistry, different structures. And this will be the question, the most the most challenging. Okay, thank you.
Thank you. Philippe?
Yep. Just to comment and to come back on the discussion regarding the inspiration from weather forecasting. Of course, you already said that it can be an important source of inspiration. I think especially for communication. Yeah. For instance, the fact that they provide a single solution or a single model. This is something we already discussed a bit yesterday. And the way they are using also to communicate their uncertainties or their probabilities, as Mitro just said. So I think it's important to have a look on that side as well. But on the fact that they provide only one model, this is the way it is. But in the meantime, what is possible and what maybe a lot of us are doing as well is that we can consult and we can get various forecasts from various sources. So you can have a look to. In a way, it's like looking at several models as well. There are even applications providing forecast from various models of forecasting. So in a way, we are not in a different way than that. But what seems to be sure or quite evident is that for communicating to the public, communicating one solution appears to be the best solution. Yeah.
Well, depends on the public also. Yes, Charlie?
Microphone. Yeah, on the communicating the one solution, well, maybe I said something confusing. I mean, I meant to say that the weather forecasters, they always have multiple models. And what they communicate, I think, it's not really one model, but more like a summary of the statistics from all of these ensemble members. But okay, when you see them on TV, I think they'll have a display of the best estimate of the weather, but they know in the background they've got all these ensemble members, and they can say what the probability of rain tomorrow will be based on how many ensemble members is it raining in tomorrow, basically. Well, okay.
And by the way, Lawrence,
Dmitro, we have another person who raised the
Lawrence Attractor. I wanted to mention you that it exists.
Steve?
Yeah, just on the weather thing and the probabilities. So the weather forecasters don't really tell you much about uncertainty. So they may be running multiple realizations of multiple models. They do have an extraordinarily large computer, and they are blessed with fantastic data going back more than 100 years. So they don't have the same sort of problems that we do. When it comes to uncertainty, you never see things like the probability of sunshine is 5%. They only show probabilities for rainfall because people are interested in rain because they need to know that's going to change their behavior. It can be expensive for companies. But there is a bias on this as well. And you will notice that they will never show there is a 50% chance of rain. And the reason for that is because the public don't like 50% chance of rain, because that sounds like a guess. if the probability is high, they'll tell you that. If the probability is low, they'll tell you that. But I challenge you to find an incidence where the probability of rainfall is 50%. So there is a bias. And their communication of uncertainty is highly specific.
Yeah. Okay, thank you. Philippe, or I understand, yeah. Charlie, would you just like to?
Yeah. In the discussion we have now regarding probabilities and so on, just as Charlie said, for the weather forecast, there are various models behind and so on, and the one solution that is proposed is in a way the most probable solution. And this is something we can do, and we do in 3D geological modeling as well. And I'm thinking about the capabilities of inverse modeling by coupling geology and geophysics. So this is something we do, and we are able to make some probabilities on the solution of this inversion, because with geophysics we don't have a single solution. So when we take in the inverse problem at the same time geology and some parameters or some measurements in geophysics, such as gravimetry, for instance, it is possible to make some probability. So we can also provide a single solution for a 3D geological model describing geology, and of course we can do that describing density, for instance, because it's in the process of the inversion. So we can provide a geological model that is the most probable. Looking at the voxels, for instance, if we deliver it as voxels, we have the most probable voxel that is possible considering this inversion we provided. So this is also something we can do in geology.
Yeah, correct. Steve, I think you are the first one now to respond.
I didn't actually take my hand down from the first time.
Okay, so this would be Rasmus then.
Yes.
Rasmus, if you would like to comment.
Working, but it was just to add on to the discussion about weather forecasting. Is that I think there's also a distinction in that, at least in the near future, for weather forecasting, you can actually get validation of your model results, which is not something we can do to the same extent for geological models.
Okay, Charlie.
Yeah, I think it's a good point, but I think I sort of disagree with it, because we can always drill a new borehole, for example, and see, collect data on the bits that we hadn't seen before. And another thing that we could be doing that I don't know if we are really doing is we could be creating our geological models, like specifically holding out 10% of our data, say, and then comparing how well does the model match that 10%, basically doing cross-validation. But I don't know how much that's done in how we're working with geological models. So I think, well, my impression is that in geological surveys, we're generally throwing in like all the available information into making our geological model of the country. But then that leaves us really no way of gauging how good is that model for predicting in areas that we didn't already see. Whereas if we did cross-validation, always intentionally holding some data out, at least while we're developing the methodology for the modeling, then we can gauge how good is our modeling methodology at making predictions in unseen locations.
Okay, I think I saw a couple of years ago there was a talk among modelers about this kind of validation, like taking some data out, and then I don't remember exact examples where someone did it and actually did validate the model like that. Steve, do you still want to say something now?
Yeah.
Because
Yeah, I was going to say that everything that Charlie said is right. The whole sort of bootstrapping thing and leaving out data is tremendously important. I have seen in Australia, I've seen guys doing that. Not in the oil industry. In the oil industry, you tend not to have enough data to do that. What I don't see is when somebody drills a new borehole or a new well, I don't see anybody ever looking at that data and saying, how good did we do? How good was our prediction? I've never, ever seen that. And you're right, Charlie, you could do that every time you get some more information, every time you get some more seismic, you could do that. Going back to the weather thing, partly the reason for that is because data is very expensive in the oil industry and mining industry. To collect that data is expensive. You're collecting it to make a decision, and there is immense pressure on making that decision with the new data, not working out how good your process is. In the weather situation, you have all these weather stations recording data every day, amateurs and professional stations alike. And it's incredibly easy to do the bootstrapping. It's incredibly easy to look at all the weather stations that you've got and say, how well did we do? And the Met Office are probably doing that every day. And they know how good their forecast is. And that's why their forecast, their predictive capability is improving far faster than ours. We're still moving on geological timescales, basically.
Well, weather forecasters also get better and better resolution models, and that includes also the terrain models that are getting better.
I was involved in a project in Brunei where the weather forecast in Brunei is awful. There's only one weather station in the whole country, and we were trying to put weather stations in every school so that we could understand the local climate variability. Once you've got that, then you've got the capability to work out how good your predictions are. And that's the key to improving your modeling.
Okay, yeah. Rasmus, did you wanted to say something? Or your hand is up because...
Oh, no, sorry, I didn't put my hand down. But
okay.
It's just, yeah, I think, yeah, I agree that we can always drill a new borehole, but it's just comparatively much more expensive and single point observation compared to, say, we get meteorological data each day. So maybe it adds on a little bit to Steve's point that their models get so much feedback all the time in comparison to ours that they can improve faster.
Yeah. Philippe?
Yeah, on the discussion of excluding some data from the 3D geological model, I confirm this exercise has been already done, but it's quite complex or difficult because usually we have a lack of data. So if we want to exclude some of them or one of them, it's especially at depth, of course, except in some very particular context, geological context or areas, we have more information on the surface than in the underground. And from what I remember, when this kind of exercise was done, of course, it gives a kind of uncertainty or the capability of the model to predict what happened in the borehole you have excluded for the computation, but it applies at that location, at the location of the borehole. When you want to deal with the rest of the area, once again, depending on the kind of context, if you have a very complex geology where the geometry is very moving and so on, I'm not sure it will give you a broad overview of the reliability of the model if you just exclude one borehole somewhere. In fact, it will give you some information at that location, but not really elsewhere. Yeah.
Okay, so now I think it's David. Yeah,
if going back to meteorology and comparison with geology, the thing is that meteorological models work that way, that they have a global model, regional model, and then local models. So they go from big scale to small scale. And if you look at the geological modeling, we often work in the other way around. We have a target area, we model it, and then often we don't calibrate it or align it with the regional conceptual model or so on. So I think it's one of the biggest problems for especially working in the Alps is at this point that we don't have a reliable regional evolutional model of how this knapsacks and so on happened. And it's therefore even, I think in certain way we can assign or we can describe where the uncertainties are, but it's really impossible to give it a numerical value or anything like this.
Yeah. Charlie?
Well, okay, I guess a few things that I want to say following that. Well, I don't know. I'm finding this conversation really juicy because it's like the intersection of, I don't know, a lot of things that I find interesting. But anyway, that's just me, I guess. Yeah, so Philippe was saying about the sort of leave one borehole out cross-validation, and then this tells you something about your prediction for that location in particular, but it doesn't necessarily generalize, I suppose. But I would say, well, in statistical modeling, I think you have to kind of specify the framework or the system that you're using to construct your model. And then you can use the cross-validation to assess how good were your uncertainty estimates. But I think maybe in the geological modeling, maybe there's a general issue that we struggle to kind of, I guess, mathematically formalize what the procedure actually specifically looks like. So if we can't automate it, then it's difficult to run things like cross-validation, because ideally you would formalize the procedure and make it something that's automatable, and then you can then apply that procedure on any subset of all the data that you have, and you can compare how well does it perform and how well calibrated is its uncertainty estimates on any other subset of the data. And I agree with the point that's been made that, okay, it's expensive to drill a new borehole and we can't always do that. But as countries and as Europe, we have so much geological data. There's plenty, I would say, to be able to be doing cross-validation with. But I think that the bigger issue, or the kind of hurdle to get there, is that we probably need to be able to like formalize the model into like a mathematical procedure that's run on a computer. And this is what the weather forecasters are doing. Guillaume mentioned like that they've got the equations for the behavior of the atmosphere, like Navier-Stokes equations. We don't really have necessarily equations for geology, but there's no reason why we can't. Well, okay, yeah, maybe that is a reason why we struggle, essentially, that we don't have this kind of physical equations to use in our models. But now with things like machine learning, we ought to be able to machine learn geological behavior, I guess. Well, there's more I can say too, but I don't want to go on for ages, sorry. Yeah, people have talked about the cheapness of weather forecast data or weather data in general. Yeah, there are loads of weather stations. There are, yeah, there is a lot of weather data, but I don't think it's necessarily cheaper for them. For example, a lot of the data in weather forecasts come from satellites, and those cost absolutely multiple millions or billions of pounds to put into space. But they've managed to do it because they're good at justifying to funders why those satellites need to go up. And I think in geology, we could become better at justifying to funders why we need to collect more data to support, for example, these kind of ensemble models of geology, which would quantify uncertainties and provide more utility to stakeholders than I think we've been able to provide so far. And things like the current importance of critical minerals could be a good kind of avenue to pursue that with. And I think with the right coordination, we can make the case that we need all this investment that the weather forecasters are able to get. And it's also been mentioned that, you know, the weather forecasters have the biggest supercomputers in the country often. But again, they didn't just get given that out of luck. They got kind of awarded that because they justified the need for it. And again, I think we've got a need for it here too, but somehow we haven't been so good maybe as the weather forecasters at making the case for needing these technologies. That's what I was thinking. Thanks.
Thank you. Well, the need is there, but I think it's in Europe, it's in a sense new, because we try to put all our mining industries overseas, you know, and now we are reverting to the idea that we do need to mine in Europe. So yeah, we would have to make a compelling case and show that we can use this money as well, right? So yeah. Invent procedures to really be successful. We still have just 2 minutes, and I feel like it would be nice to at least have a look at one other question from the Mentimeter. We had a ranking of situations which were like projects incurred significant costs due to insufficient information. Clients incorporated uncertainty into their decision making, and the one that actually got most votes was the one which says uncertainty is discussed more for 3D models than for 2D maps. And I guess in a sense it's kind of makes a loop to what Ferdinando wanted to talk about as well in his questions. And I saw him raising the hand just a while ago. So I wonder if you want to say something, Ferdinando.
Yeah, I can comment on that. So I raised the hand because I agreed on the comment made by David before regarding like these global models that could help then the details. And that's exactly the philosophy why we are building this big scale in the Alps, big scale model in the Alps. So then that in the future, we can use this as a framework to then build more detailed ones. And that's exactly the strategy, and connects as well to what Charlie said before, to attract also more funding. So if we have a better picture that is less defined, difficult to put numbers on it, it's also probably easier to then attract and say that in this place we have better chances than for future projects. So by having this large scale picture, we can then move to the next after, let's say, 2030 planning, and that's the strategy behind. And regarding the maps, yeah, you have seen that for us, it's really like before I heard there is plenty of data. Yeah, I don't know, not everywhere, plenty of data. Like there are places really, it's a bit empty, the subsurface in there for reasons. It's very expensive to do anything there. If you don't plan a new railway or highway tunnel, then nobody's very interested. But the maps are actually crucial and they present all the problems. But to dive in and dig a little bit more in the uncertainty of them also could be very important thing. So probably, hopefully we are planning to do that also in by us. Let's see what we can do on that. That's what I wanted to say, sorry.
Yeah, okay, thank you. Well, Philip, and I think we will need to finish the session after your intervention.
Yeah, but just a quick comment on that. Regarding this difference between how we look at maps and how we look at 3D geological models, I think there is a cultural side on that as well, because I think that we really used to use maps, and they are there for decades and even more. And at the time they were down, even the recent one. There wasn't this discussion about uncertainty, probability, and so on. well, there was this discussion, but not in the delivery of the product, I would say. And now we are talking about 3D geomodels, and the culture has changed as well, I think, and we are much more regarding about accuracy, probability, and so on. The maps were really considered, once again, on a cultural point of view, as the reality, or as what we know about the reality, even if any geologist knows that a single point on the map hasn't been observed by all the points hasn't been observed by the geologist doing the map, of course. But I think that there is also this it's more like a cultural or philosophical point that is related to this perception, at least, of how we look to the map compared to the 3D geological models.
Yes, thank you very much. I think with this we should wrap up the session. We saw quite a few very nice case studies. We didn't have time to talk about everything, and I just wanted to maybe add just one point, that if we think about equations and automating things, well, the presentation by Jan, the first one from TNO, used that at least to some extent. Anyway, let's finish with this. We talked a lot about other disciplines, mainly meteorology, to help us handle uncertainties, and we saw quite a few very nice examples. And thank you very much for this. Thank you for joining. It was a pleasure to chair the session, and let's see back again at 2 o'clock for the next session on communicating uncertainties. Thank you.
Thank you. See you at 2 o'clock. Yeah. Bye.
Thank you.